talk actually to some people I haven't met before, which has been very exciting over the last days. So, in terms of the subject, I was aware that I have here mathematicians and geophysicists, and so I sort of designed, I hope, a journey into inverse problems in seismology, where I will sort of intertwine some precise mathematical statements with some more seismological perspectives to inverse problems. So I hope I can reach out to both communities up to a degree. And so pretty much will be an overview of inverse problems that really look at the mantle. It's by no means a complete story, but pretty much looking at inverse problems at greater depth, if you wish. Various collaborators have contributed in various papers that I will cite. Elena Barretta, Elisa Francini, Gen Nakamura, Otmar Scherzer, Günter Ullmann, all mathematicians. Of course, long-term collaborator Rob Vanderhilst, and Anders Washi, Sergio Vesela, and two students, Jia Shi and Zhang Jai, have contributed to various parts of my talk. So this is basically the summary of the talk. And the rest is an illustration, a justification of the statement that I make. So if we look at inverse problems from a seismology point of view, what is sort of common practice? Well, first thing people would do is they do imaging. Imaging is based on a perturbation. And so imaging is very much making an assumption about the Earth, how it looks like, and you try to correct for it in a perturbative sense, and that is your image. It's a difference between sort of an a priori model versus what you hope to get in addition to the a priori assumptions. So imaging, linearization, all these ideas fall under the category perturbation. And so you might argue, well, that imposes a strong bias in terms of the model that you use. And so can we do better than that? Should we be doing that? Do we believe the results? Moving beyond perturbation, people have been doing optimization in all sorts of flavors. But the optimization, the problem is, if you do not have any understanding of uniqueness, of stability, you really don't know what you optimized. You'll generate a picture. And the picture will have started at some initial assumptions, an initial model, and will go somewhere. And you can regularize, you can do all sorts of things, but you create a picture, and you have absolutely no idea what really the meaning is, at least from a mathematics point of view. And so that leads me to the question, what you really need to study before doing anything like that is you need to understand the anatomy of inverse problems. If you cannot control how to sort of think about the inverse problems from a uniqueness and stability point of view, you perhaps shouldn't even start to begin computing. And I hope I can convince you of that paradigm. So here are a few more details saying essentially the same thing. I'm going to focus on three categories of inverse problems. There are more, but just to keep the talk concise. I'm beginning with looking at the spectrum of the Earth, the eigenfrequency. Then we'll look at high frequency data, meaning time domain, transient phases, and then we'll look at strictly bounded frequency data, which is essentially the time harmonic, the elliptic point of view. So these are the three I will discuss, and we discussed these problems from the point of view of uniqueness. I must immediately disappoint you that the state of the art for an elastic Earth is actually it's pretty limited what we know. And I will give you basically an insight of what we do know, and also where our knowledge at the moment stops, which is very much an area of research. We know mathematically and intuitively that these problems are ill-posed. And so anything related to computations will run into trouble, optimization for example. So we'll really look at conditional stability that should be better than ill-posedness. Exponentials should be, say, typical of the type of Lipschitz or Hölder. And that's sort of a central theme in the talk that I'll give you quite some details about. And then, of course, if you take a mathematical journey here, you have to greatly worry about the fact that with partial data, we can only measure in dense, well, in the best case scenario, dense arrays on continents and nowhere else. And so, in order to get this conditional stability, we have to look into the equations that describe seismology. We have to look at their coefficients, describing the properties of geomaterials, we have to look at them by looking at structures. By imposing certain structures, which you can think of some sort of vague prior information, these structures will become necessarily multi-scale, we can hope for actually achieving this goal. So the idea is if we don't know about uniqueness in general and we have no stability, then look at structure and keep these structures as general as possible. So I will build up the Earth from a very coarse structure, a very symmetric structure, to more and more details, to as rough structures as we can today in my talk. And well, here's a summary of the inverse problems that I've selected to talk about. The first inverse problem is the eigenfrequencies, what we call mathematics is spectral rigidity. Do the eigenfrequencies actually determine the properties, the wave speeds, the elastic parameters of the Earth? And of course, in general, we would expect no. Then I will move on to high frequency data and talk about nonlinear, strictly nonlinear tomography, but with discontinuities. So we are adding some complexity here. Then I'll make a little detour, more historical perspective. If we simplify the problem greatly and make it separable, we come into the world of imaging, the more classical world of imaging. And I'll show you a little bit, like if you do that precisely, you will also get some interesting results, though it's not solving the inverse problem in its entirety. And then the last, but a good part of the talk will be what do we do sort of beyond what we call adjoint tomography, waveform inversion, optimization. So can we actually do something that is much closer to an iterative reconstruction? And so I will give you actually ideas how we can guarantee convergence and meaning of reconstructions if we do it in the right way. And this all leads to hierarchies. So going through this list gives a hierarchy of structures, there's a multi-scale nature. And the multi-scale nature, though not really established yet, has natural connections to homogenization up to a degree. And so one thing you may wonder, if I introduce coefficients with structure, this really comes out in mathematics, sort of an abstract argument. But this is where you can get great help from the physics. And so what is an interesting path to take is say, well, once we have this understanding, can we link this into physics and come up with perhaps a more constrained description of coefficients on the basis of that rather than the basis of achieving conditional Lipschitz stability of these problems. So that's sort of in very general terms what I'll discuss today. So let's talk about the inverse spectral problem. So simple question, Prem. Is it true? Suppose we try to determine Prem from the eigenfrequencies alone. How can we think that this holds any truth? And the story is, of course, ancient. If I only detect the eigenfrequencies, I cannot solve this inverse problem in general. This goes back to arguments of cuts and others. You cannot hear the shape of the drum. So let us do something different. And this is actually a very recent result. Let us step back and say, let us assume that the Earth is only radial. So let's take the simplest representation of the Earth, spherical symmetry, isotropic. And let me make the problem local. So let me say, well, I'm looking at a family of radial models. I'm not expecting that I can recover a model from scratch, but within a family I can try to determine what the right Earth model is. Is that uniquely determined? And so that's what we call local rigidity. And the answer to that is actually yes. And this is actually a very new result. And I thought I'd give you a quick insight why this actually can be true. Perhaps the most fundamental question, I would say, in normal mode seismology. You can actually get unique information with certain conditions from the eigenfrequencies alone. Of course, what I assume is that it's radial, so I assume that I know the shape of the Earth. So I also assume that I know the shape of the core mantle boundary, I know the shape of the inner core boundary. If I didn't know that, this could not be unique.
Does that mean that you can get the shape of the one-dimensional drum?
Right, exactly. Which I call radial, because I have to assume symmetry. It's actually true for general radial manifolds. It's a slightly more general theorem, but yeah, that's correct. I don't have to assume smoothness. In fact, speeds can be C11, and I can assume discontinuities. So I build it up from NLI, and I can glue annuli together. So I can have an inner core, I can have an outer core, I can break the mantle up with a transition zone and so forth. These sort of things are fine in the argument, but it needs to be symmetric. So how does this argument go? And I'll give you just a sketch. I'm not going into any proofs or details. I want to give you a feeling of some of these problems. So basic calculation, the mantle is, well, it's the difference between two balls. Mathematicians, of course, set the radius of the Earth equal to 1. And r is, let's take the mantle, so r is the radius of the core mantle boundary. And so this is the mantle, the difference between two balls. So I remove anything that is below the core mantle boundary, introduce spherical coordinates as usual. Gamma r, these are rays, or geodesics, so I'm talking here now geometry, high frequency. And they are labeled by small r, and small r is the closest point to the center of the Earth at theta equals 0. So think of it, you have a turning ray, and so there's a turning point in the ray, and the turning point is the closest point in the center of the Earth. That's what I call r. So small r indicates sort of the turning radius in this particular setting. And so r, well, that must be somewhere between the surface of the Earth and the core mantle boundary, defines a ray. And, well, as follows, it's a map from time. Time is the length along the ray, travel time, in spherical coordinates. So what I call L is the half length, so it's all symmetric, so rotation is symmetric. So I can think of a ray that goes from the surface point to the surface point. I can split it from the turning point into two halves. So this part is L and that part is L. So that is indication of the length. So it's the half length of a ray. And of course, this is a simple calculation of rays in the radial Earth. This is the calculation that you find. This is the expression for the length. And what I call alpha is the angular distance between the endpoints. So if I think of alpha, it's an epicentral distance in some sense. If I have a ray and the ray comes back to the surface of the Earth, then alpha is precisely the epicentral distance, angular epicentral distance. So this is sort of the setting. And so how do they look like? Well, here we have some rays, periodic rays, that correspond with toroidal modes, particular toroidal modes. For n equals 4, L equals 40, so the overtone 4, angular degree 40. And I can, of course, change the frequency, and here you see how these sort of rays can look like. So what you're searching for next are periodic rays. Periodic rays have everything to do with eigenfrequencies, and I'll argue that it's an ancient result from the 1960s. Let me immediately remind you that in general, say if you add heterogeneity to the Earth, we don't even know where the periodic rays exist. We don't even know that in a triangle, in general. So, but of course in spherical case, this is known, this has been known for a long time. So what are sort of the conditions to make the uniqueness work? The key condition is what we call the countable conjugacy condition. So what does it mean? If I look at the following problem, I need to assume that there are only countably many radii, turning points, between the surface of the Earth and the core mantle boundary, so that the endpoints of the ray that reaches this turning point, which is the maximal ray, the maximal geodesics, so that the endpoints of the corresponding maximal geodesics are conjugate along that ray. So conjugate means two rays come together into the same point. So it's associated with caustics. So think of conjugate points as have rays that sort of connect to the same point. So the number of radii, turning points where that's happened, must be countable. That is the key assumption mathematically. Now this is in fact very, very close to the old Hertz condition. If you're familiar with travel time tomography, I'm not going to do that detail, but it is a Hertz-related condition. And of course it's satisfied by Prem. If you wonder, is this condition actually realistic? Well, any sort of standard radial model that we work with satisfies the countably conjugacy condition. So what does that imply? What is an important ingredient? Well, let P be the set of radii for which the corresponding rays, turning rays or broken rays, are periodic. So now I'm going to restrict myself to rays that close, somewhere to the same point. They can bounce around many, many times, but eventually they come back to the same point, so they're periodic. So restrict yourself to these radii, these turning points, that are associated with rays that are periodic. And they form a set P. And so P is a subset, of course, between the radius of the Earth and the core-mantle boundary. On the other hand, let C be the set of radii for which the endpoints of the geodesics are conjugate. So they form a caustic on the two sides, so they come back to the same point. Then, with this condition, the following is true. By the way, C is nothing else as these radii for which the derivative of the angular coordinate equals 0. It's a quick way of understanding where caustic is formed. If I have the countable conjugate condition, the following is true, that if C has an empty interior, then P is dense. And what we need is denseness. To be precise, this is one always implies the other, but if the wave speed satisfies this countable conjugate condition, then C and P are countable, C is closed and P is dense. That's what you need. That is what we're doing. So in other words, what does it physically mean? If there is somewhere an annulus in the Earth, a thin annulus, with a low wave speed, and I can trap a ray that basically cannot go out or cannot go in, I'm in trouble. That means that region really is an obstruction to uniqueness. Well, that's what you sort of physically expect. So sort of very much related to non-trapping, this condition. And so how do you proceed? How do you actually, what are the ingredients to prove it? Well, what you use is what's known as geometric quantization. This goes back to Keller and Rubinov in the 1960s. And the geometric quantization is roughly speaking as follows. Due to the symmetry, all the rays in a symmetric Earth are restricted to a plane that contains the center of the Earth. So it's essentially a two-dimensional problem where you just rotate the plane around. So that's the first observation. The mantle is an annulus. Now if the rays turn, if they reach the turning point, I have rays that come in and rays that come out. And so that means that if I track the travel time along these rays, these travel times are multivariate. So what you do is the reasoning of Keller and Rubinov. What you do is you disentangle that by not defining a travel time on an annulus, but defining a travel time what they call a covering space. You make copies of it. And so what you can show is you need a couple of copies of the annulus. Of course, the points in interior and exterior connect, so they form a torus. And so in fact, the covering space is a torus. And then the geometric quantization is nothing else that if you take any closed curve on that torus, it needs to be quantized, but there are only two independent ones. Like if I have a curve on the torus that is sort of encircled the central hole, then I can change the radius, I can deform it, but it doesn't really change. It can smoothly deform one into the other. So I only have the closed curve that is just any closed curve around the central hole. And the same is true around the body. So I can sort of play around with that, I can deform it, it doesn't have to be a perfect circle, but there can all be smoothly perturbed into one another, deformed into one another, so only one of them really is important. So these are two independent closed curves. And so they need to be quantized, so they need to satisfy a quantum number to form the spectrum. And the quantum conditions are that R0 is the turning radius, this ratio is L plus a half over the frequency. And so P0 would actually be the ray parameter of that ray at the turning radius. And the second quantization condition relates to travel time. So L is half the travel time, and this is the sort of the travel time in some sense projected along the surface of the Earth in angular. So this is sort of, if you think of radon transforms, this is like the intercept time, the radial intercept time. And that should be quantized with an overtone number. It's the angular degree, and that's the overtone number. And these 1/4 and so forth are related to the count of caustics. These are KMEH indices. And so if you substitute L, you get an integral relationship. And so what do? Well, this goes back to the 1960s. In order to find the spectrum, to relate the spectrum to closed geodesics, what you do is you extract P0 from the first relation. So you substitute P0 from the first into the second. So P0 is expressed in terms of L. Here you see P0, but it contains omega, so I get an equation for omega. So it contains L and N. I solve that for omega, and I get my eigenfrequency omega and L, overtone number N, angular degree L. And once I have that, I substitute it back into the first quantization condition, and I get the ray parameter that actually generates a closed geodesic. And so I'm done.
that an exact result or an asymptotic result?
It is what they call an asymptotic semi-classical result. So it's not true for the lowest frequencies. But the beauty is we don't need the very lowest frequencies. But in fact, if you do an accuracy, it's incredibly accurate. I mean, asymptotics kicks in from n equals 3. It's a high L asymptotic result, semi-classically. But L doesn't have to be very large to make it a few digits accurate. But mathematically, you don't need more than this. So mathematically, you're fine. And so essentially, it gives you, so what we call the length spectrum in mathematics is the length of the period of all the periodic rays. Okay, so I can make many periodic rays. Of course, I'm not interested in rotating them because these are the same. So all the independent periodic rays have all a different length, and a collection of all these lengths is what we call the length spectrum. And so essentially the geometric quantization gives you a relation between the length spectrum and the eigenfrequencies. So that's the key thing. And as you can imagine, I can perturb this argument as well. I can differentiate this argument. It's still true. A little bit of technicalities aside. And so here comes basically the rigidity result. So I have the mantle. Take a family of models, radial models, in some sort of interval minus epsilon, whatever that epsilon is. It's some sort of small number. They all C11 functions, satisfying the necessary condition. Then the following is true. If the length spectra are equal, so the length spectra in this entire interval equal to C0, then all these C taus have to be equal to C0. So it's uniquely determined. That's a precise statement. This is joint work, actually, recent work with Jonas Ilma Virta in Finland. Now, you can do this separately for turning S, you can do this separately for reflecting, inner reflecting SES, and so forth. They all actually give the uniqueness separately. So you have actually redundancy in the different modes in that sense. So this statement is true. Now, how does a quick side remark? When you look at these problems in spectral rigidity, it is a standard argument which we also have in seismology, in the symmetric case. The following is true. If I take the normal mode summation, I take the trace, then the trace gives me this expression. This is some of the exponentials of the eigenfrequencies. And in fact, if you look at where the singularities of these expressions live via Poisson's formula, the singular support is the union of all the length spectra of all the particular modes, S, SCS, and so forth. And so, by looking at this, what we call the trace formula, by looking at the trace formula, you not only via geometric quantization, but also via the trace formula, you have a relationship between the length spectrum and the eigenfrequencies. So it goes via geometric argument. Now then you have the right tools. Then you say, well, forget about the eigenfrequencies. I have a billiard transform. I have periodic geodesics, so this is a billiard transform. And so you can work on machinery for the billiard transform. And you can prove injectivity via a relationship with some kind of Abel transform. So you go back to Abel transforms to prove this injectivity. Now what is essential is that the rays, these periodic geodesics, are stable under perturbation. And so in a radial Earth, in a radial manifold, you have plenty of them to do that. In a general Earth, that's not true. And so you know immediately that if I add arbitrary variations, angular variations, I'm certainly in trouble. But there might be certain Earths where it's true. And just to refer to an extreme case that we're working on, suppose you take a manifold of negative curvature, which, well, cannot be an Earth, it can be a very general subject, then almost surely the same result is true as well. So you're not stuck with radial Earth, you're stuck with the fact that these periodic broken rays need to be stable under variations in the wave speed. That is the key thing to make it unique, rigid. So that was the story on the spectral part. So that's the question. I mean, can you go beyond a radial model? It's not known, certainly not in generality, but there are probably some generalizations possible. But let's make a little sidetrack. One of the curiosities would be, can we actually compute these normal modes in generality? So another track is a track where we try to actually solve eigenvalue problems on a very, very large scale. So take the Earth and discretize the Earth in an unstructured tetrahedral mesh. We'll go in that direction as well, typically you might have up to 1 billion elements. Find the eigenvalues of a billion by billion matrix. How do you do that? So the various projects on that, and let me just say a few words about it. It is not as simple as it sounds, not from the computational point of view, but not from the mathematical point of view, and it's because we have an essential spectrum in the Earth. So things like core undertones and so forth, I'm not going into the details. This essential spectrum causes a major obstruction to straightforward computations. So you need to go to quotient spaces and so forth. But once you understand the essential spectrum, you can follow a radial width approach. You have to deal with how to incorporate this quotient space. And then really what we do is joint work with Dan Sorensen, who is the author of ARPAC, to shift invert method of solving eigenvalue problems that are not in standard form. That is essentially how the normal mode equations look like. And really what it is based on is you couple this, you have an inverse of the matrix. We actually do this inverse via a structured factorization. So the way we do this, we use particular structured matrices to factorize the matrix, not the frontal approach. And we can do that by a completely randomized numerical linear algebra. So you can let the matrices disappear. And that's why you can do these extremely large problems. So it has become feasible to actually compute normal modes, in principle, in the Earth. And so I just show you some examples. So this is how an Earth can look like on an unstructured tetrahedral mesh. And here we are computing for a particular perturbation of PEM, the stony mode, the core mantle stony mode on this unstructured mesh. This is the 2s16 mode, but we can also compute inner core modes and so forth. So we begin to be able actually to compute normal modes on a global scale, to my knowledge, for the first time in its full generality without any assumptions. But the inverse problem remains open. So let's move on. So radial Earth, we might argue we can recover in principle the radial Earth. So let us add more structure to it. So the simplest structure we can add is we have discontinuities. Let these discontinuities sort of vary in topography. And let us assume that we have some smooth angular variations. So the Earth is not an onion, not a perfect onion, but I have some variability. Can I solve that? The answer is yes, you can do that with high frequency waves. So that brings me to nonlinear tomography with discontinuities. And so, well, the data are, well, high frequency phases. So they're essentially geometric. We are essentially looking at in what directions the wave arrives and when they arrive and where they arrive. But you can use waveforms for that matter to detect that. So we assume here that the Earth is piecewise smooth, finite set of interfaces, and it need to be known that they are there. So you do not need to know where they are, but I need to know the number of them. That is a prior information in this type of result. But unknown speeds, unknown shapes, and there are a couple of conditions to get unique recoverability and a stability estimate. And I will argue that these stability estimates are extremely important if you want to do iterative reconstruction. So that you can think of as a very precise optimization. Stability gives you convergence in optimization. And so what are the type of conditions? So roughly speaking, what you do is, first of all, you need diving waves and reflected rays. You cannot do with either of the two. And the way you do it is to say, well, take this as the first discontinuity. And what I do is I take a copy, I reflect the wave speed of above, say, the first interface, in that interface to the interior. So what you see here is not the core mantle boundary, you see some sort of wave speed that is geometrically flipped around in the interface over here. So I turn a reflection into a transmission. Now the price you pay is that ray, so if you have a discontinuity, I take the mirror image, it is only discontinuous in the derivative. So it's no longer discontinuous in the function itself. So you have a Lipschitz wave speed, and that is what helps you to make this work. And so what you need to do is you need to understand whether I can uniquely recover the functions, the unknowns, of integrals along rays where the rays in the background have discontinuities at all the discontinuities that are assumed to be there. So how do you deal with that? So it appears to be the case is you can get a uniqueness result by assuming that the distance between interfaces, between discontinuities, is not too large. Now it doesn't have to be epsilon, it is a constant that appears, constant order 1. but I cannot choose them arbitrarily far apart. So I need to have a sufficient number of interfaces to do this. In practice, that number is actually not so large. And then the other key condition is this type of condition. So I have reflected and transmitted rays. I take a point, draw a ball, I take any direction on the ball, plot the plane normal to that direction, then there needs to be at least one ray that is tangent to that plane that doesn't hit conjugate points, doesn't go through the caustic, but only one. So in 3 dimensions that is perfect, because I might have a hotspot somewhere, like a plume, if they exist, but then if this ray would go through it, I can choose another direction and avoid it. So as long as I can find corridors in the Earth where I can avoid, by choosing a ray that it doesn't hit the caustic, I'm fine. And I need to be able to do that for each direction, but I only need one. So I need actually very, very few rays that behave well in some sense. So if that is the case, then again you can prove unique recoverability. It makes use of heavy microlocal machinery of paired Lagrangians, operator mapping properties and so forth. And how it really works is you do the tomographic inversion nonlinearly in one go. So what happens is you do your tomographic inversion of in a classical way. I pick out the singularities. The singularities are the level set function of the interfaces, and the smooth functions are the speeds. So I reconstruct everything in one go, but I can detect what's the singular part of the reconstruction of the smooth part. And so in one go, I actually can determine the topography and the wave speeds. So I've resolved any ambiguities that would exist between the depths of the interfaces and the wave speeds in between them. Of course, under these conditions. So that's how far you can push that. Now a few remarks. Yeah.
Is that last result, is it just isotropic models? Or?
Yes, this is isotropic. Yeah, so far I'm just building up the complexity. First it was completely radial isotropic. Now I add some angular variations in the problem. And then we'll slowly build it up from there. You're far from anisotropy. Yeah. And so let's make a little detour on older work, separable inverse problems imaging. Now, imaging is a very, very powerful tool, but again, it's perturbative, it's linearized, and the second thing is you assume a complete separation of the material properties variations into 2 scales. There's nothing else. You might strongly argue against that, but if you assume that, and if you assume that sort of linearized scattering is what we observe, then you can image, and you can prove things and so forth. And so this is an old picture of early work of us. Essentially, what you can do in the separable inverse problems, you can look at the derivatives, the imaging kernels. So take a simple model with a discontinuity and a low velocity lens. The imaging kernels consist of 2 separated parts. One is related to recovering discontinuity, and the imaging kernel is this isochron, finite frequency isochron. And recovering this low velocity zone is a very coarse scale. Looks like a tomographic ray. These are the fat kernels that are associated with wave equation tomographic imaging. But they separate in scales, and if they perfectly separate and it's all linearized, then you can, under certain conditions, disentangle this problem and solve this problem. And so for fun, I'll show you actually a very recent result with the group at MIT, where we went back and we sort of disproved PREM below 660 in the transition zone. So even if you follow a separable inverse problems approach, you already find things that deviate from PREM. And so what do? We look at inverse scattering. So here we are under the Pacific. We are studying already for quite some years Hawaii, the hotspot under Hawaii and its surroundings. We're going to look, roughly speaking, under Hawaii. We're looking at SS precursors between, well, here and here. The events are over here and most of the stations are US array, but of course we can go a little bit around. So we do an inverse scattering transform that I will skip over if you haven't seen it. It is just high frequency linearized inverse scattering, generalized radial transform inverse scattering. And what you see there on the left is if you just do an inverse scattering and you create image gathers for different angular distances. Now, I don't want to go into these details, but I would like to show if you do that with full power of the inverse problem, if the separable inverse problem, you can get pictures that solve the tomographic part independently of the discontinuities. So let's look at the discontinuities. Now, one thing we did over here is we, for reasons in this picture we can clear, we try, normally when you do imaging here, you start this, by the way, these are multiples, the 410 and 660 multiples. So what you normally get is you get an interference of phases for smaller angular epicenter distances. So what we did here is we used a very careful argument using wave packets to do the imaging, separated for multiple scattering, multiple interactions with the discontinuities at 410 and 660 and a single scattering. And it gave this image. And so what you see here, so what we said, well, let us do we did a very precise analysis. Let us have a look what we can obtain from this. Well, we can obtain topography and so forth. But we can actually start to look at the reflectivity. We can actually start to detect a very high resolution picture, the reflection coefficient. And perhaps the most remarkable thing to see here is if you follow the geometry, the singularity of the image, which is plotted along the dots at 660, you see that it's red here and blue here, and vanishes here. There's actually the zero crossing in the reflection coefficient. And so this zero crossing in the reflection coefficient, which you can see because of the separation of multiple scattered events, constrain you, for example, to separate shear wave speed and the density below the, in this case, the 660. So for fun, I show you a picture what sort of things you can begin doing. What you see here are essentially reconstruction of the reflection coefficient at the 410 and the 660. Let's focus on the 660. This is the angular range where we get a stable image. And what you see over here is there's a zero crossing in the reflection coefficient. And so you can then from that determine the density and the shear wave speed. Contrast, I should say, across the 660. And so here's prem. These are the confidence ellipses of this reconstruction. And so you see that the prem completely deviates from the, in fact, it doesn't predict the zero crossing in this reflection coefficient. Now, there are some other studies, what I just would like to mention. If you believe this result, then our prediction, when we cross the 410 and from below up into this, across the 660, then if you look at the composition of the mantle there, it should be actually a mix between pyrrolite and picklogite. So the usual pyrrolite models are actually off from these estimates. So there are all sort of interesting avenues to look at and look at it on a particular corridor in the Pacific, which we are doing as we speak. So these sort of things, these sort of high resolution reconstructions you can get by showing separable scales in the right conditions. But it's very restrictive and it assumes many things. So let me go to the last part. So let's go to the parts that look, let's make a jump. Can we make things more general? So can we actually do reconstructions where we don't have radial symmetry, we don't assume piecewise smooth, we want to make the Earth rough. How rough can it be? Well, the interesting thing is, the idea of working with high frequency data is out of the window. So if you study inverse problems in detail and you would like to take the limit of frequency going to infinity, you can study carefully what happens. Anything that you study in terms of the inverse problem essentially blows up. So you need to take the point of view when you add roughness that I need to cut off the frequency in the data. It sounds counterintuitive. You add more complexity, you want more resolution, you actually have to cut off the frequency. There's nothing to be done with high frequency data. So once you take that paradigm, of course, the inverse problem is nonlinear, so you're not lost. It's not like a linear argument, and the linearity allows you to gain. So how do we view the data? What can we precisely say about this problem? So let me show you what you need in the arguments to get results. You need a notion of a Neumann to Diagonal map. So what is a Neumann to Diagonal map? It's essentially you take the elastic time harmonic, say, wave equation, you apply a traction and you measure the displacement. And you measure that in the same set. So how do you do that? Well, of course, if you control sources, you put vibrators down and you put geophones down and you're done. You do exactly that. How do you do it with earthquakes? Well, there are a couple of options. What you can do is you can say, ignore the main part that you observe after an event. We look into the coda and correlate the coda and then the rays at the surface. If the right centers, in principle, you can recover locally the Neumann to Diagonal. What you can also do, but we haven't done that, if you have many, many earthquakes and they're sort of randomly distributed, which they aren't, then you can actually probe the surface and you can generate the Diagonal to Neumann map from that point of view. So there are ways to obtain that, but it requires massive, massive data analysis, data processing to do it. But what can you say? This is what you need to make actually any statement. So this is an example in the crust. If you compute such a map, you apply the boundary source, attraction source, and you observe this is a particular component of the displacement. So that's how these time harmonic problems look like. So let's stand back for a moment to explain a few results. What do we know for the scalar case? So we get a Helmholtz equation. So think of that as a proxy to the p-waves. So what's a Dirichlet to Neumann map or Neumann to Dirichlet map? I apply a boundary source of a particular support, and what I observe is the normal derivative of the solution. So that would be the displacement to traction instead of the traction to displacement. But these are related to one another. So that is a little detail. And my forward map maps the wave speed to the operator that maps the source distribution, the boundary source distribution, to the array data. So a very important thing is never look at the data themselves. The problem should always be formulated in the operator that maps sources to data. So let's call that operator F. And so what we like to do is understand the inverse problem related to this operator F. So what can we say? So essentially what we can do now is we can go and partition the Earth in a sort of an unstructured T2 domain. Do a domain partition of some sort. And what I'm going to assume is that there are very simple functions defined on these partitions. Constant, piecewise linear. So they can jump everywhere, but they're very simple functions in each particular subdomain. And so my claim is that problem we cannot only uniquely solve, but we can solve stably. We can make the Lipschitz stable. So what is happening? So, well, I need to, of course, make a few assumptions. Mind you, here we're staying away from the spectrum. Okay, so what we first did, we looked at the spectrum. Now we stay at frequencies in between the spectrum. Because that is where all the arguments blow up. In particular, if you study Fouché derivatives, the problem they blow up if you get close to the spectrum. So you need to stay away from the spectrum. Once you start to do reconstructions, that will become iterative reconstructions. So this is a domain partitioning. Essentially, all I want to say here is I take some sort of simple basis, like piecewise constant, over, say, n subdomains of the Earth that can be unstructured. And with that comes an approximation error. So if I approximate the Earth with such a representation, then the real seismic data will be an approximation because I approximated the Earth. So I have an error. And eta is the error of that particular model if I knew the true Earth, which I call C dagger. Now what I need, of course, the bound in the Fouché derivative appears here in how accurate this is in terms of the approximation of the model. So the approximation of the model translates into the approximation of the seismic data. And you can have a bound. There's one constant that appears here. But what will appear to be important is, as n becomes large, I need to be able to get rapidly better approximations of the Earth. I actually need a convergence rate that is fast. I call this function phi. So think of it as wavelets and image compression, or compressed sensing analog, is in the arguments I will need that I can represent the Earth very, very well by increasing n, but the approximation improves very, very rapidly when I do that. That's the compression part. So described by the eta and the data. So what can you prove? You can prove that I can solve this problem uniquely. So we take two models of the Earth. These are the two data sets of the Earth for fixed frequency or bounded frequency. It's the same result. It's elliptic essentially. And so it's a Lipschitz stability result. And of course, I'm not going through the proofs, but what's a key ingredient is the three spheres inequalities, unique continuation argument to establish that. And you can do that for partial data. Now I said, okay, that is interesting. What about the ill-postness? I know the problem is ill-post. Well, of course, the ill-postness is hidden in the constant. So what happens if I increase n? If I make a refinement of the Earth? Well, the constant will grow exponentially. And in fact, the constant, you can prove, will grow as an exponential with the number of domains, discretization of the Earth, n in the power of 4 over 7 in dimension 3. And so here comes the game that if you want to use an iterative scheme, the radius of convergence of an iterative scheme, if you design it properly, is inversely proportional to the stability constant. So the stability constant is very large. I can optimize, reconstruct, Landwave iteration, projected steepest descent, whatever. I can construct it, but I need to start very, very close to the true Earth. Otherwise, it's meaningless. If the stability becomes very small, we have a very large radius of convergence. So n, in part, n controls that. It's also controlled by frequency. It's primarily controlled by n, by the number of elements. And so the idea is, by looking carefully at the estimates for this constant, we're going to play a game, a multi-scale game. So the idea is, well, let me first reconstruct a very coarse model of the Earth, and very small. Large radius convergence, large approximation error. Let me get to the projection to that. Be sure that I'm in a convergence radius of the scheme. Now I say I switch gears. I'm saying I say a starting model, by changing the frequency, I can change the convergence radius. If I guarantee that that convergence radius is a larger n, I can actually reconstruct a projection to a larger n representation of the Earth. So all I need to guarantee is that I have a nesting of radii of convergence by increasing n and slowly increasing omega. And since we have an expression in the constant, we are completely in control to do so. So that's essentially what you learn from what I call the anatomy of the problem. So going back to my first statement, optimization, I believe, is pretty meaningless. But if you do iterative reconstruction, knowing these results, I can guarantee if the Earth is there, from where you actually are able to converge to the right Earth or not. And so I give you some pictures. Well, here are some statements about this nesting of radii of convergence. If you're interested, there's a paper that gives you the entire algorithm how to do that. I'm not going into the details. It's a multi-level projected steepest descent generalization of an algorithm designed by Ingrid Dogen-Shi and collaborators. Numerics, it's sort of stunning when you see it, you say, well, there's an unusual power in the exponential. Here's a numerical verification for different frequencies that these exponential powers are real. So it's an extremely accurate, it's actually a sharp estimate mathematically. And so numerically we have confirmed that. And so we're going to use it. And so let me show you a toy example, our standard, everybody's standard basic example. So here you have, this is just a geological model, Marmusi. I can start this from a very simple one-dimensional model. I'm actually in the radius of convergence. And so by nesting the radius of convergence, this is piecewise linear, increasing n slowly, then increasing frequency, I can converge essentially to the model, multi-scale. So it's scale coupled multi-scale, but the scale is really the represented domain partitioning. So of course you can do this in 3 dimensions, gives you an idea. These are 3-dimensional structures that we can recover, very high speed contrast here from low to high. We have very little information within the radius of convergence. On the left you see horizontal slice, on the right the reconstruction. And even the vertical layering you can recover extremely well. So this technique gives you complete control over these problems. So it gives you a complete understanding of how to do iterative reconstructions rather than just optimize blindly. You may immediately argue that, well, this is all very interesting, but I assumed a given domain partitioning. So my prior information was that I gave you a partitioning of the Earth, whatever it was, and it prescribes to you how I'm going to refine it. Every time I increased n, I said I'm refining here, 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 here. So that might not be quite fair. So the question is, can I actually recover this domain partitioning stably? Well, here we have to pay a price. So you can prove a different result. Say, well, yes, you can. I can do it if it is an unstructured tetrahedral mesh. Well, it doesn't matter, it's a very general unstructured tetrahedral mesh. I can do it if the wave speeds live in a finite set. So I have 5,000 values of a shear wave speed, and I prescribe to you that there are only these 5,000 values possible in the mantle. So under these conditions, and that the mesh is not too, but the mesh needs to be regular. I cannot have sort of elements in the mesh that are extremely thin and extremely long. So there are certain conditions that appear that sort of break the recovery of the mesh. But other than that, I can actually locally recover the nodes in the mesh, and I can even recover the number of elements. But again, what I now assume is that I have a predetermined set of possible values for the wave speed. And so, what is the way it works?
To clarify, you mean that it's actually a finite discrete set, not just that it's bounded?
That's right. It's,
okay.
This is a finite discrete set of wave speeds. That's correct. Yeah. Precisely. Now the number can be relatively large, but it needs to be finite.
I'm confused as to why you would, maybe this is a stupid question, but why are, normally in these kinds of problems, you would just choose a mesh, and you just use it. So,
You mean in your computation or in the inversion?
oh, I don't know.
In your computation, you would choose a mesh,
Yeah.
in the normal conditions.
Yeah,
In inversion, you don't really know how to choose the mesh, because the mesh will sort of determine sort of the region in which you're going to converge.
Oh.
And so in this case, I want to remove that prior information. And so I want to say, look, so what is the idea? What are sort of the competing mechanisms? So the ill-postness is hidden in the exponential growth of the constant e in the power n4/7. So I need to begin to work with low n. So if I have few n, the initial partitioning plays a role. What's going to happen? And so I want to fix it. I want to allow it to change before I increase n. And so that's how I remove in some sense the parameterization. Not quite, because I still assume this tetrahedral, I assume that it's piecewise constant linear, but I don't assume anymore that I know exactly the vertices in the mesh. And so it's only for the inverse part, not for the computation. The computation you typically would have to refine. So the mesh would be too coarse even to do any computations on. Okay. And so how do you do that? Well, you control that via the Hausdorff measure between meshes. And what is that, roughly speaking? You look at the distance between vertices and you take all the permutations. I mean, that is a technical detail. And so the inversion in this case looks very much like Hausdorff warping, except it's done on seismic data. And so the theorem is that if you take the Hausdorff distance between these two meshes, they are Lipschitz stably recoverable from the data under the assumptions that I mentioned. And so does it work? An example where I show you the recovery. If you see the following recovery, don't only look at the surface here, this particular surface that was chosen as an initial surface. So this was sort of an initial, if you wish, segmentation of the Earth. You thought there was something there and you started that way. That is the initial model, if you wish. Don't only look here, and the scale refinement, also look at the tetrahedrons around it, because they will change and update at the same time. And so this is sort of what happens when you do the core scale reconstruction, the finer, and the finer. So you see the scale refinement taking place. So these are the reconstructions you can do. So mind you, it looks perhaps like quite a stunning reconstruction, but I started already with a segmentation like this. So there was already a pre-existing segmentation. But then, so it's a local result, it's not a global result. But locally you can do very, very powerful things nonetheless. That gives you an idea. So, final words. What about the elastic Earth? And the news is pretty bad. In the case of the elastic Earth, isotropic elastic Earth, we don't have a global uniqueness result, even under the most idealized conditions yet. The most recent result that we've proven, is if I have perfect boundary data everywhere on the Earth, and if the Lamé parameters are smooth, or few derivatives, reasonably smooth, then we can uniquely determine that up to a finite dimensional subspace. It's mathematically an interesting result. In practice, we are not there yet. However, if we assume an unstructured tetrahedral mesh, and we assume that the Lamé parameters are piecewise constant on an unstructured tetrahedral mesh, can be multi-scale, can be large, then actually with partial data, with data say on continents, we have a uniqueness and a stability result. So in that case, we do. And so essentially what you can show is I have two Lamé parameters, the density, take the L infinity norms, take the maximum of all the differences. They depend linearly on these type of data sets. So we can iterate, we can recover, we can do the same things we did before in a multi-parameter setting. But mind you, I should have a word of warning. You think, well, these meshes are incredibly general. Piecewise constant functional meshes. You can build very, very general Earth models. Mind you, they are not dense in L infinity. So by no means this means that I can reach any rough function that represents the Earth. So the story is still incomplete as it stands. But this is pretty much the status quo of what we do now. And well, the techniques go via particular singular solutions and again quantitative estimate of unique continuation. And then you do, the beauty is since the Lamé parameters, it's sort of an interesting physics in mathematics. The Lamé parameters appear in the leading order derivatives of the equations, density in the lower order. And so that allows you to do sort of an alternating estimate of proving the uniqueness. So you can actually determine the density as well as Lamé parameters in principle, in this case. So of course this is piecewise constant, tetrahedral, and so forth. And so this gives you a quick picture of what you can do. So this is structure with a sort of tubular feature. I wouldn't call it anything. This time is actually designed as a test model in the Tom's group in Princeton. Here you have the P S-way speed and density, and here you see sort of how you can reconstruct. So this is the true model, these are the initial models, and this gives you the idea. This is a cross-section, three-dimensional model that indeed you can separate very different behavior of parameters following this gradual increase of M multiscale, increasing the frequency according to the nested radii of convergence. So you can really do this problem if the Earth is well approximated by these sort of models. And so where we are heading, time is up. So this is essentially what we're really doing. So I'm not showing you in full glory all the computations we're doing. So what we can do is, in the process of working with these meshes, we can do, of course, multiscale refinement, coarsening, and topological change. So if you look at one of our meshing reconstruction algorithms, here you see, for example, how we can actually zoom in an automatic fashion and change the topology of the mesh. So there are a lot of things going on. How do you do that? Use particle methods, Warren-Moy cells, and dual graphs. So the multiscale nature of the Earth on a tetrahedral mesh is really defined by particles. That is the way you can control it. We use for discontinuities embedded level sets, which seems to be natural, and then the rest already I mentioned. So here you see, for example, how we can deal with topological changes in these meshes. So this is sort of what we're doing as we go along, and this is what we're working on, is essentially rebuilding an unstructured mesh of the Earth while we're gathering power in computations, and a lot of work to be done on the data side, of course. So, but this is the beginning of that stage. And so let me just end with an outlook. Perhaps come back to the beginning. So the anatomy is very much connected to structures and the coefficients. If you want to say anything, if you want to mitigate repulsiveness and so forth. So think of the domain partitionings, the segmentations, the meshes. These are mathematical meshes. These are not numerical meshes. They are really mathematically controlled. And so interesting questions are, where can we connect this to physics? I mean, this is a natural platform for homogenization techniques. Homogenization techniques could tell us how we do this better than just using it as prior parameterizations. And so, well, it brings us to questions as feasibility of a global reconstruction. In principle, yes, but a lot of work, pieces to be done. No information really of anisotropy in general yet, though some things we do know. What is very important is, I didn't speak about this, sampling criteria. A lot of people are greatly worried about sampling criteria, rightly so, but we are really in a position that we need to do something else. I mean, the seismic setting will never be such that we can satisfy sampling criteria. So what we've been working on, a totally different direction research, is we work on information-based techniques, and so that brings you to techniques from deep learning. So when you look at data as an operator, applying many boundary sources to arrays, in fact that operator is incredibly redundant. The trouble is we cannot describe that by analysis tools. We can cut out the dimension, but if you cut out the dimension, obviously you lose generality of the applicability or the structure of the inverse problem. So how can you specify that? So we have followed the route with Stéphane Alain Paris and collaborators to look essentially at deep learning structures of these data. The same you can do for the inverse problem when you iterate. So you're finishing your paper and doing a deep learning actually in doing some sort of super resolution of the inverse problem. So there are things lying underneath when you enter probability that you can do that are way, way beyond working with these particular model parameterizations. It's a subject by itself, very exciting. So we're definitely not at the bottom of it, but I do believe that you need to go these routes beyond what I've spoken about today. And this is the end of the journey that I wanted to present. Open for discussion. Thank you very much, Maarten. Questions? David?
So I had a question about the first part one.
Yeah.
Eigen frequency reconstruction.
Right.
And it's essentially to do with finite data And I
Yes.
have in mind these from memory sort of results in spectral geometry, like if you're given a finite increasing sequence, you can find a manifold, which that's the spectrum of the Laplacian.
That's right.
So, do you have any sense here of, given a finite number of eigenfrequencies, what you can constrain?
It's a very good question. I don't have a sense. I believe, in general, you will fail to get uniqueness. But I think your question is a little bit finer than that. You say, well,
Is there a neighborhood?
exactly, is there a neighborhood? Is there, subspace where you can think of, well, to have sort of a coarser representation of the radial profile that I can still uniquely recover. We don't know that at this point yet. And in fact, I can map this back to an even more elementary question. Like when you do tomography of the mantle, like we've been doing for years, we know very well that we cannot really recover the deep mantle. Any picture you see from the deep mantle is tomography. I wouldn't trust. I leave that to other people to give their own judgment, but none of that makes, with the pure techniques they apply, like the local linearized approach, like basically, this X-ray tomography in a fancy way that you can do. There's no way you can deal with that. Now the question is, can I understand where exactly the limits are? Can I project that onto sort of a multi-scale subspace, directional? In principle, I believe you can solve that problem. We haven't quite done that yet. And so that might give an insight in the spectral counterpart. But that is the building principle. But that is still way out to say something like that. What I would argue, on the other hand, is what I'm more interested in at this point is these deep learning algorithms where you say, I don't have enough directions. Can I, in a probabilistic sense, from the right point of view, actually bypass that problem? So can I, in a probabilistic sense, still get the necessary information where the resolution is not damaged, except I don't know the exact realization anymore in some sense. I think that's the better way to go, because the other part will never be able to solve with whatever acquisition we do of the surface of the Earth. And the other approach has potential.
Do you have any further questions? Sana?
Well, I just have a question about the bit of actual data I saw.
Right.
I was wondering, is it fair to say that the estimate of impedance you came up with is a minimum estimate due to incoherent stacking of the data?
Well,
Just the amplitude.
yeah, so of course there's a lot of processing underneath going on. So you're probably talking about the fact, suppose you don't have a perfect core scale model tomography, so that means you don't have a perfect alignment in integration. And if it's slightly off, it's sort of the worst case scenario, because you would sort of minutely change the amplitude, because we're looking at that relative variation of amplitude. So yeah, of course we did the best we could in terms of being very careful how we did that. What we also did is we did an estimate. So suppose it is off by a certain percent, what is sort of the percentage in the relative amplitude error we make? And in fact, the error bars you saw are primarily the error bars due to that.
Oh.
Not due to noise or anything. The worst thing is precisely what you say. But the error bars are,
So the topography was accounted for?
yes, it was accounted for. But you still have error bars. I mean, yes, the best you can, but it is not by no means error-free. Now, I should immediately say the beauty is that zero crossing that can move around a little bit, that is sort of the key. That's why these ellipsoids are so narrow. The fact that we could detect the zero crossing of the reflection coefficient is sort of the, that's the key thing. And that very beautifully nails it. And for that we had to do our entire wave packet imaging. Otherwise you cannot disentangle these multiple scatter phases. But yeah, a lot of subtle processing has been going on.
David?
So I had another question relating to the Schlechter-Neumann
Yeah.
sort of map you had, and you had kind of mapping h to the half to minus a half,
Right.
which I'm guessing that's an important
Yes.
aspect.
Yeah.
So suppose you had not the traction data but just the displacement, then you wouldn't have it would be more smoothing. Would that
Yes.
affect things?
Yes, it would affect things. I didn't want to go in details in sort of the misfit you use. So you can do a little bit better than, well, better in a sense. I can sort of loosen things up a little bit from that. If I assume that I know the wave speed at the surface of the Earth. Of course, it's a bold assumption, but think of it, you do mantle studies, you sort of homogenize the upper part of the crust. If I know the homogenized value near the boundary, then actually this operator becomes a Hilbert-Schmidt operator. And so I can actually use a Hilbert-Schmidt norm. I can prove that it's equivalent in that case.
I guess what I was thinking, sort of more generally, is that we don't really measure tractions, at least in
No.
an obvious way.
No.
So is that going to always be an essential part of?
What you can show is that this is equivalent to what we call a single layer potential operator. And so that means you can recast it in a different data set. And so no, it is not essential, but you need to replace it via different boundary source distribution, which is still not trivial to get. I'm not saying that, oh, this is all not an issue to do that. But what we really do in these computations, actually we use these equivalent single layer potential operators. So these are sort of, the kernels of which are really like sort of fundamental solutions, but not on points, but on the right finite energy functions, boundary functions. So that is in principle sufficient. I make some sort of weak statements here. But still to get it from, so what we have been working on is using the coda of large earthquakes. With Michel Campillo, this is ongoing work. So the usual idea, the correlations, you play with many variables in these correlations. And you start to correlate, and indeed you start to see these sort of fundamental solutions appear, which generate these kernels. Of course, you have to average over the number of big earthquakes that should be sort of distributed in some sense around the Earth. And of course, you can make things, when you look at the right spot with the right earthquakes, and you can make that work, I think, quite nicely. But in general, there's a lot of work to be done there, because that won't be sufficient to sort of cover large parts of the Earth. You have to look probably at the strategy of using weak earthquakes and using many of them, and assuming some sort of random distribution of them, and then correlate these results along these lines. We probably have to go to make that rigorous. So a lot of work to be done. You probably know Victor Tsai. He's been at Caltech, so he's been working on these correlations as well, looking at the reflections basically all the way through the Earth. Again, it's all done under very favorable playgrounds, if you wish. So by no means claims that this is going to be, the solution tomorrow to these problems, but there are some very nice, I think, results that indicates, well, it should be in principle within reach, and this is how it should be done if you want to do it. There's not much alternatives. Again, optimization by itself, I think, has limited value.
Okay, on that note, can I just thank, you got a quick one.
Well, very briefly.
I need to get to a nursery.
I can answer
Go on.
some. I just was interested in one particular slide because I didn't catch what you were exactly plotting,
Yeah.
which is on the plots of the Stony mode that you were showing.
Oh,
But I just missed what it was you were exactly plotting.
I was actually plotting one component of displacement of an eigenfunction in 3 dimensions.
Yeah.
And I believe in the Stony mode I plotted the radial component in that picture in color. So let me see. Go back. Yeah, that's the radial component. Yeah. So of course we don't have polar coordinates really in our calculation because we have an unstructured mesh. So what we did in this case, we just artificially projected it into a radial component. We just compute in some reference frame the vector locally in a Galerkin approximation sense.
Right, I think I should call time here. Of course, you're welcome to carry on the discussions when I'm gone, but I do need to get to a nursery. Thank you very much, Maarten.